So I've got your homework assignments. Probably everybody wishes they had a little bit more time to work on it, right?
Yeah.
So if I gave you until tomorrow at 9 a.m., would it be a good learning experience, or would I be saying, procrastinate your homework, it's okay, I might give you an extra day? See, I'm balancing, like, do I be generous or do I be...
Salvage our homework grade.
I don't care about the grades, I care about how well you learn, and I think that...
Well, I actually understand, like, the process. Like, I was trying to do it in Excel, just like we did the in-class exam.
Yeah, it's not an Excel problem. As I mentioned in class, I haven't figured out a way to do it in Excel. All right, so I'll tell you what, if you'd like to retrieve your homework at the end of class and get it back to me tomorrow by 9 a.m., that'll be fine. All right? But I don't usually, that's an exceptional thing, and I know that you realize that. So, what's that, Zach? Yeah. Okay, so your next homework assignment will be due in class a week from today, and then the first exam is 2 weeks from today, also in class, Tuesday the 25th. And we're going to continue talking about the Hardy-Cross method today. We're going to set it up with Excel, and then we're also going to verify the solution using water gems. And you've used water gems before, and so maybe it'll be a little bit of a refamiliarization, but this will be one of the nice chances to see that Excel matches up perfectly with what water gems calculates as far as the pressures at each of the junction. So in the second example, things are going to get a little bit more complex, because instead of just an R value that stays constant, like it did in the first example where I was just familiarizing you with the structure of how the solution proceeds, this time we're actually going to allow F to vary. And F is going to update in each iteration based on the velocity and Reynolds number from the previous step. So the columns that you should use in today's spreadsheet are a little bit different from the columns that you set up in example 1 for Hardy-Cross, because this time around there's going to be an F value column that is based on the Reynolds number and the corrected velocity from the previous step. So you will use fully turbulent flow for iteration 1 to find your first set of F values, and then starting in the second iteration you should use Jane equation to calculate F. Once everything converges and your percent change for the flow rate from your initial incoming flow rate Q and the corrected Q, when the percent change is down below 1% and you know that you've iterated enough and the solution is converged, after that you're going to calculate the head loss through each of the pipes so that you can find the pressure at each of the junctions. So here's the network that we're going to be setting up. You can see that there are 2 loops. There's more pipes than there were before, but that actually doesn't complicate things as you might expect. Having extra pipes doesn't make the situation too ugly. We've got a certain K sub S for each of the pipes of 0.3 millimeters. Now each of the pipes, all of the junctions are on the same horizontal plane, and so the elevation doesn't vary. And that's important when we calculate the pressures. The pressure is known at one junction. Here at this control point, I say the pressure is 600 kilopascals. But once you find what the flow rates are and how much head loss there is through each pipe, you're going to be able to calculate what is the total head and therefore what is the pressure at each of the junctions. So one of the things that I mentioned here is that you're going to start off by manually identifying an initial flow rate and direction guess. So for example, you've got 1 cubic meter per second coming into A, so you're going to have to split some of it down that way, some of it this way, and do the same thing at DF, at DC. That should be your the first thing you do as you get started, not to type in column headings, but is to do the flow rate balance at each of the junctions, and do it with a pencil on the handout that I've given you. And if you want me to check that before you get started, I'd be happy to, because that's another one of the frequent problems, is that if continuity isn't satisfied when you start off, then your solution can never converge, no matter how many iterations you do or how well your spreadsheet's set up. So that's an important first step. Now here's the solution. This is what comes out of the end of that spreadsheet, and I've got the values there in your handout for you. How you, at the end, have the certain corrected flow rates and the head loss through each pipe, and then you take that head loss to calculate the head at each junction and therefore the pressure at each junction. So we're going to be sort of working at different speeds. I'm not going to have everyone on the same page at the same time today. I'll be circulating around, and I imagine some people will finish this sooner than others. One last thing is there's an announcement at the end of the class notes that I've given you about a research opportunity for some funding from Dow Chemical. And so read through that letter, and if you're interested in doing research, you can talk to me or to any of the other faculty members, depending on maybe what subject area you're interested to perform research in. So I just wanted to make you aware of that opportunity. So you're going to start off with the flow balance. That's the pipe length and the pipe diameter. Other questions? All right. All right, let me just remind you of a couple important, like the commonly made mistakes, is that for the first set of F values we're doing fully turbulent flow, and remember that the sum of these, you know, when you have all of the R times Q times absolute value of Q, the delta Q is negative of this divided by that, and you have to type the formula in each time. You can't have it anchored to these cells because you're going to want to copy this whole set of rows and paste it below, and the only way for that to work is if each time you type in the equation so that you can copy and paste the entire block together. And then the other thing to point out is that for percent change, you have the difference, so in this case it looks like the new minus the old divided by the new, because we're assuming the corrected Q is better, is the right answer. And so the percent change will be the difference divided by the new value. And then this Reynolds number is what you're going to use in the next set of iterations down here once you start utilizing Jane. Now the other thing is common pipes. There are two common pipes. There's EF and there's CE. And so you'll notice that here I threw away my guess flow rates. Even though I had a guess flow rate that I came up with when I was splitting it on the paper, I'm not using those even in the first iteration for loop 2. I'm using the corrected Q from the other loop. But besides that, I'm still using my guess flow rates from when I did continuity across the entire paper map. All right? Here's the example. I'm going to work through the solution. Starting off, we look at the flow balance. Now remember, as long as continuity is satisfied at each junction, your flow balance can be anything you want it to be. I took sort of the easy route, and I have 0.5 cubic meters per second coming here, 0.5 cubic meters per second, because what comes into A has to go out. And I look at the other inflow. I've got 1.2 cubic meters per second coming in. I have to have it coming out, and I split it evenly among these two pipes. And so this is defined, and this is defined, which tells me that 1.1 has to come out of junction F through this pipe EF. And if 1.1 is coming into junction E and 1.6 is coming out, that tells me I have to make up the balance of 0.5 by a flow from C towards E of 0.5 cubic meters per second. So then at junction C, the 0.5 out is defined, this 0.6 coming in has previously been defined, and that leaves me with a balance of 0.1 cubic meters per second going upward from junction C towards junction B. And then finally, as a check, I make sure that the sum of the flows at junction B are equal. And so the 0.5 cubic meters per second and the 0.1 equals the 0.6 that's indicated. The other thing that's given in this problem is we know the pipe lengths and diameters for each pipe. So for example, pipe AF is 180 meters, its diameter is 400 millimeters. All of the pipe characteristics related to the size are known, and it's provided at the beginning of the problem that the K sub S for each of the pipes is 0.3 millimeters. So with that, I'll scroll down to the column headings that are used to solve this problem. Let me zoom out a bit now that we're not looking just strictly at that image. All right. Let me delete the things that are already there. Okay. So we've got the known pipe characteristics that are entered into the table here. Make this a little bit bigger. All right. The first thing I want to do is use the fully turbulent flow assumption to come up with a guess F value for each pipe. And I can do that by starting to type in the Jane equation, but just forgetting to include that right side term where it has the Reynolds number. So let me type in the Jane equation, 1.325 divided by the logarithm of the K sub S divided by 3.7 divided by the diameter. And I need to square that. All right, 0.174, and that's a guess value based on fully turbulent, and ultimately I'm going to, in the next iteration, start using the Jane equation. So let me just drag that down. I've got an F value for each of the pipes based on it being fully turbulent. R is just going to be the F value, F times L divided by D divided by 2 divided by G, 9.81 divided by A squared. All right, and that gives me an R value. Now I know that for some of you this whole divided by so much is a little bit confusing, so let me just put it as this. FL divided by D FL divided by D times 2 times G times A squared. And you get the same 10.1. All right, so I can drag that down for each of the pipes. Now the N value here is 2 because we're going to be using Darcy-Weisbach as our friction equation. If we were using the Hazen-Williams, it would be 1.85. And now for the Q's, in the first loop, first iteration, I just put in the values that were the basis of my original guess. Now remember that clockwise is positive, so by definition, a positive, let me do this, a positive direction is, sometimes it's hard to draw using the tools that they give you. Let me see if I can do it this way. That's my positive. That looks nice. That's positive direction. All right. So, for example, pipe AB is that direction. So I'll say 0.5. BC. Now this is up, which is against the clockwise direction. So I'm going to say negative 0.1 for BC. CE, that's in the same direction as clockwise. So 0.5. EF. EF is against that, so negative 1.1, and AF also against the positive direction, so that's negative 0.5. Now, down here, I'm not going to fill them in yet because CE and EF, these are pipes that have a common, those are the pipes that are common to both loops. And so I'm not going to even bother typing in the Q values for them because I know I'm going to get them from the corrected Q. But I can put it in for CD and DF. So
CD is going to be negative, because you can see it's going up, and my clockwise positive would say that down is positive. So I'm going to have negative 0.6, and then over here for DF is positive 0.6. All right. Now R times Q times the absolute value of Q, and I can drag that down for all of them. Let me just reduce the number of numbers that's showing so that I don't get all those hash marks. Here, I'm going to need to know the sum of everything above it. All right, and now N times R times Q. N times R times the absolute value of Q. And I'll drag that down through all of them. And here, though, I want it to be the sum of everything that's above. Or I could have just said, this formula is the sum of everything above, so I can just drag it sideways. All right? And now the delta Q is going to be equals negative this divided by that. I have to type it in each time, since I want to copy and paste later on and have the relative positions remain correct. Okay, everything's fine and dandy there. Let's say we've got our original Q plus the correction factor. So now we have a corrected Q. Of course, the absolute velocity will be the absolute value of Q divided by the area. All right, so now I've got velocities. And the Reynolds number is V times D divided by the kinematic viscosity of water, which is 1 times 10 to the minus 6th. All right, so now I've got Reynolds numbers there. And the Q change is I'm just looking at this guess Q compared to the corrected Q. And so I'm going to say it is the new version of the Q minus the old one divided by the new one times 100 to give it in terms of a percentage. All right, and this gives me an idea of how close to convergence my solution is. The answer is not close yet. Okay, so what I need to do is put in some flow rates for pipe CE. It's going to be based on this value. Instead of going with my initial guess when I was just setting up the guesses for CE, remember I said it was 0.5 that way. So if I had typed that in to my second loop, then I would have said positive 0.5. Let's see. But what I'm really going to do is I'm going to say equals negative of that. I think it needs to have the number of digits reduced so that it's consistent. Equals the negative of the most recent one for EF. All right, that's good. So now I can do the same thing where I sum these and have the column next to it. I need a sum for that as well, and then my delta Q's will be equals negative this divided by that equals negative that. Okay, great. Now for the corrected Q, it will be the original guess of Q plus the correction factor. Drag that down, and then the velocity, I can just copy these. I don't need it there though. It calculates the velocity for me. Same with Reynolds number. I'll just calculate or just copy and paste and and all it's doing is just applying the Reynolds number based on the velocity from that same row and the diameter from that same row. And I can do the same thing with percent change. Just copy 4 of them and it'll apply it to the next 4 down. So the percent change is still pretty big, but it'll converge quick enough. Now I'm going to copy everything again. So I'm just going to copy this whole block, and I'll make some updates along the way. Copy, Control C, and down here Control V for paste. Now this is going to be iteration 2. And I'm using Jane for the F value now. And so since I'm using Jane, I'm going to dispense with what I've got there, and I'm going to change it to include, over here, I'm going to have to add the 5.74 divided by the Reynolds number. And the Reynolds number that I'm going to be using is this one that is from the previous iteration. So if I go up here, it's that Reynolds number to the 0.9 power. And that gives me an updated value of F. It didn't change a lot, but because the fully turbulent flow assumption was fine. Let me drag that formula for F down all the way through. So it's using the output Reynolds number from the previous iteration. Now, technically, for these common pipes, remember CE and EF, I could here go get the Reynolds number from there, you know, from the same iteration but different loop. But the fact is that the F value is already so close that it doesn't really matter. So I don't have to be as meticulous about accessing the most recent Q. I do have to be meticulous when I'm accessing the most recent Q, but with the F value, since the F is already pretty stable, I don't have to do anything other than use the Reynolds numbers from this first iteration. All right. Now I do need to update the Q's because previously they were just typed in. So for iteration 2, the most recent version of the guess for the flow through AB is going to be up here. Let me zoom out a little bit. Well, I'll just refer to that. Now I'm going to zoom out so I can see things more completely, you know, bird's eye view. Okay, the most recent BC is going to be this one. Most recent CE equals negative of that flow rate, because that's one of my common pipes, as is this EF. And then the most recent AF is from here. I need to go down, and the most recent CD will be that one. CE equals negative of this corrected flow rate, equals negative EF, and equals the most recent DF, which is here. All right, let me just glance over my solution to make sure that everything's as it should be, and it appears that everything is fine, with the exception this CD here. Oh, yeah, I did equals the negative when I shouldn't have. Let me correct that. You only do the equals negative when you are referring to something that is common between both loops. So with that, I think everything's in good shape. EF. Did I go get that corrected Q? EF. All right. And it looks like I made a mistake typing in the formula for this AF as well. It should have been, so for getting the updated AF, it's not a common pipe, so it's just going to be equals the most recent flow rate, which was that one. All right. So it's only for these pipes that are bolded, which they are the pipes that are bordering both loops, that I need to change the negative sign. Okay, so what I want to do is take a look at making sure that for this flow rate it is from the same iteration, and it is the same iteration. It is. You notice that the Q change is decreasing nicely. Alright, so let me do iteration 3 now. I'm going to copy everything, Control C, and then I'm going to just paste it, Control V, and let's see, I'm going to change that to be iteration 3. Now the important thing is you have to maintain the same number of spaces from iteration to iteration, or else things can get a little bit messed up sometimes when you're doing this convergence kind of thing. But I think that I've copied and pasted with the correct number of spaces. I don't think there's any problems here. It looks like my percent changes are getting smaller. That's a good indication. Let me Control C and then Control V again. Here I'm in iteration 4. And my flow rates aren't changing. You look at the delta Q, it's so minuscule, that tells you that the corrected flow rates aren't going to change. If the delta Q is so close to 0, then the input Q and the output Q are the same. The other thing is that you look at the F values from iteration to iteration, the F values aren't changing, right? 0.178, 0.178. This one's changing a little bit because the flow rates are so small. But this pipe BC is sort of a special case because the flow rates are so small. That's the only one that remains to have some percent, on a percent basis. The flow rate is still just about 1%. Okay, so let's calculate the HF through each pipe. This is the amount of head loss due to pipe friction. This is going to be in terms of meters. And all I need to do there is I need to multiply the R value times Q squared, and that gives me the head loss through that pipe. And so I can drag that down, and it tells me what is the head loss through each pipe. Now, here at junction A, it's given that the pressure is 600 kPa. And so if I want to find what is the head there, then remember that the equation for head is if the elevations are all constant and we're neglecting velocity head, it's just simply going to be the relationship between head and pressure. Head is pressure divided by gamma. And so head is pressure divided by, and this is kPa, and so I divided by 9.81, which is 9.81 kilonewtons per cubic meter. And so now that gives me here the head in terms of meters. If the water is flowing from A towards B, that means there's more head at A towards B. That's why the water is moving from A to B, is because it's moving towards a location of lower head. So that being the case, I know there has to be less head at B. So therefore, the amount of head that there is at B, it is, let me just delete all these so I'll demonstrate how you actually do it. It is the head that there was at A minus the head loss through pipe AB. And so if I find the head loss through pipe AB, there it is. Alright, so now that's the amount of head there is at B, and then the pressure will simply be the head times the 9.81 kilonewtons per cubic meter. And that tells me the pressure head at B. Now, I could have subtracted the velocity head out of there, and it would have reduced the pressure a little bit. But again, I face the trouble of which velocity to use at junction B, because you've got the velocity through pipe AB, the velocity through pipe BC. Probably the thing to do is average the two velocities and reduce that head, reduce the head by that amount of velocity head. But we'll just neglect the velocity heads because they're ordinarily a very small fraction of the total head that's present. Okay, so the head at C is going to be greater than the head at B, so I'm going to say it's the head at B plus the head loss through BC. So where's my head loss through BC? There it is. Not much, right? I can drag that down. That gives me the pressure at C. Now the pressure at the head at D, it's going to be an increase from that which is at C. So it is how much head there is at C plus the losses between C and D. All right. And let me go ahead and find the head at E is however much there was at C, because it's downstream of C. So C minus the losses through EC. And the head at F is greater because we're going against the flow. So it'll be the head here plus the losses through EF. All right, and then I can just drag this down, and that tells me the amount of pressure at each of the locations. So just to take a bird's eye view of what we did, we started off with the manual pen on paper flow balance. The flow comes in and we have to split it. We guess how much goes through each of the pipes. And we do the same thing. The flow comes in here, we split it, find out how much goes through each pipe. And then at junctions where there's flow in and flow out, that tells us how we can find out any one of the unknown flows for the pipe coming out here, or when we do this junction, then we go through the process of balancing the flow rate at each junction to find the guesses that get put in here. We use the same process of R times Q times absolute value of Q, sum that, sum this other column, and that becomes the delta Q that is added to the original guess, which gives us the corrected Q. We calculated the velocity so we could find a Reynolds number, and that Reynolds number we use later on in improving our F value guess. The percent change is based on the difference between this original guess flow and the corrected Q that we come up with. And then the only thing that we need to keep in mind is that for these pipes that are in both loop 1 and loop 2, we have to, rather than using the guess value, our original guess that was based on our pencil and paper of continuity equation, we use the updated value of Q that we found from over here. So it's equals negative of the flow rate from the other loop. And then when we bring it down into the second iteration, we're switching from the fully turbulent flow assumption for F over to Jane equation, and so that's why we've got both the relative roughness term and the Reynolds number term in our equation for finding F. But then the other thing is that the Q values we're referencing for AB, it would be this flow rate. For BC, it would be this one. For CE, since that's one of the common pipes, we say equal negative of that value. For EF, we do equals negative of that value, and so on. I hope that illustration is helpful. Again, if you have any problems or questions with the Hardy Cross example, please feel free to let me know.